Good afternoon or good morning, everybody. My name is Geoffroy Malherbe. I'm very pleased to welcome you on this webinar about robust continuous upstream bioprocessing with Thermo Fisher Scientific. Perfusion, or continuous upstream bioprocessing, comes in an evolving bioprocessing landscape where the biologics are becoming a much more important portion of the approved drugs, and process efficiencies are really in focus. Over the last decade, a tenfold increase in platform cell titers has been reported, and one of the next vehicles of intensification is going to be perfusion, right? So with that, perfusion is not a new technique in itself. It's been renewed by innovative technologies which allow to do it better and better in recent years. But it's been around for a while at various scales. And before letting the following speakers explain you how this works, the reason why it works is also very interesting. So it's a way to indeed make more biological product from a smaller footprint, but that's essentially in this way that it's known, but there's much more to it actually. And in particular, one of the reasons why it's been used historically is also because it ensures more stable conditions to the product being obtained from the recombinant cells, and it's very useful for the stability of some biological products quality. There are some challenges associated to it, which we will detail today, and you will hear more detail about how it's possible to overcome those challenges. So our agenda to talk about continuous upstream processing will consist, after those few minutes of introduction, of a first presentation from our cell culture R&D team in Grand Island related to perfusion medium considerations, prototypes, very innovative content related to the medium part, followed by a presentation from Alex Boscolo, one of our European single-use technologies field application specialists, who will take us through a single-use workflow, and in particular highlighting best practices which can be reported. And finally, because perfusion often means reconsidering the way liquids are supplied into any bioprocess, Pirkko Muhonen is going to provide us insights in supply scenarios and technical capabilities from her perspective as a cell culture field application specialist as well. And hopefully we will manage to have a few minutes for questions at the end of the presentation. Before we jump into this, I'll try to provide a very few words related to who we are as an organization, as a division, for those of you who may have an interest in that, but just really in a couple of minutes, not more. So the mission statement of Thermo Fisher Scientific is to enable our customers to make the world healthier, cleaner, and safer, very often healthier in the case of our bioproduction division, right? The whole group is noticeable first by its size and its very important innovativeness in various areas. As you can see from those figures, what's very important is that a collaborative approach brings us to help you push the boundaries of innovation. In our bioproduction division, we really focus on the excellence of cell culture steps in particular, but there's much more to it. A very important activity in the area of integration of single-use technologies following an open architecture philosophy. If you want to have a little bit more visual approach to what our division is focused on, this workflow slide may be a little bit more clear, from cell culture development all the way to bulk storage and final fill, and in a way which we understand makes our difference, which is to focus on those elements of open architecture, adaptive innovation, a holistic approach, tailored solution, assurance of supply, quality and safety, productivity, and a record of success are important areas of focus to collaborate with the bioprocessing community under an approach known as bioprocessing by design. And without further ado, I'm very pleased to introduce for the first technical part of this presentation Christopher Brau, Louise Galuski, and Jessica Nichols from our Grand Island Cell Culture R&D to take you through some considerations about perfusion medium and exciting data about recent prototypes.
Thank you, Jeff. Hello, everyone. Thank you for joining us. Today, our project team will provide an overview of perfusion as a process and the implications of that process on media design needs. We'll then discuss a prototype media we've been developing at our Grand Island, New York site, covering our general design strategy and some testing results. This section of the webinar is divided into 3 parts. I'm Louise Galuski, a scientist here at Thermo Fisher and a member of the perfusion medium development team. I'll get things started here today by providing a brief overview of perfusion, along with descriptions of the different perfusion types commonly seen in industry. My colleague Jessica will then cover some of the alpha and development work and our beta tester results. And lastly, Christopher will discuss our in-house results and the best practices to follow when screening media candidates for a perfusion process. In perfusion, fresh media is continuously pumped into the reactor vessel while culture media is simultaneously removed from it. A retention method is used to retain cells and return them to the reactor during the media removal process. In this way, the culture experiences a continuous transfusion of fresh nutrients with the simultaneous removal of waste. Medium exchange into the system is usually expressed as a rate, which is often given as the number of operating vessel volumes per day. So, for example, if 2 liters of media is being perfused daily into a system with a 2-liter working volume, this could be expressed as 1 VVD. There are different retention approaches with varying degrees of efficiency. Filtration methods, like tangential flow filtration, which is depicted here, provide the option of removing fully clarified permeate from the reactor. Settling methods, on the other hand, are typically less efficient, resulting in some cell removal, which is also referred to as bleed, in the permeate stream. Retention mechanisms are selected based on the process needs. So settling methods may represent reduced costs and lower risk of system fouling, whereas filtration methods provide permeate that can immediately be linked to further downstream processing. The last thing I'd like to touch upon briefly are active cell bleeds. This isn't depicted in the schematic, but it is important to note that some perfusion methods, usually filtration-based systems where cell loss isn't inherent to the process, employ mechanisms of active cell removal. This is done to maintain culture health in the reactor by preventing crashes and culture viability. Ideally, these bleeds are minimized as they represent loss of product and decreases in net product yield and profits. Perfusion processes can be modified to fit different needs. Next, I will discuss 4 different perfusion types in order of increasing complexity. Examples of each operating method introduced here will be reviewed more comprehensively later in this talk. We'll start with N-1 perfusion, or an intensified seed train. In these processes, perfusion is used to achieve high cell densities. This is a short duration method, usually between 4 to 7 days, and it is used to reduce the number of vessel volumes required in the seed train, allows for higher density reactor seeding, or for generating high density seed banks. Medium exchange rates are selected to maintain the culture and log growth, and productivity is usually not a consideration here. Another type of perfusion is concentrated fed batch. In this approach, filtration must be used as a retention method as both the cells and the product are returned to the reactor throughout the run. This allows for concentration of the product in the vessel and an increased final titer. This is ideal for stable products with low productivity in batch or fed batch processes. The concentrated final titer allows for more productive downstream batch processing, but the longer residence time in the vessel can lead to an increased product quality concerns. These are typically 14 to 20-day runs, and media exchange rates are targeted to generate final titers that are sufficient for downstream processing. The next perfusion method I'll discuss is an intensified fed batch. This is similar to concentrated fed batch, except in this case, the product is removed through the reactor throughout the run, making this a better option when working with more label products. Media exchange can lead to higher titer production, and the shorter residence time can provide better quality control than batch operation. Constant product removal provides the option of semi-continuous downstream purification as well. The process runtime is generally a bit longer than a standard fed batch run, so between 16 and 25 days here, and the media exchange rates are targeted to maximize the cost per titer, of course barring equipment limitations. The last perfusion type I'll discuss today is continuous perfusion. The goal here is to develop a process that maintains a steady state where productivity and product quality can be sustained long-term with minimal variability. These processes can extend from 30 to 90 days, and an active bleed is employed to maintain a targeted viability percentage or viable cell density. Ideally, this bleed is minimized again to limit product loss and maximize the net yield of the process. Similar to intensified fed batch, media exchange rates are optimized based on cost per titer. This is the most technically demanding type of perfusion. Process optimization can be time-consuming, and the long duration represents an increased risk of operation errors. It also requires a cell line with superior stability. But despite the technical challenges, continuous perfusion does provide consistent quality output of the product, so it represents an ideal avenue for long-term continuous bioprocessing. After considering perfusion as a process, two primary goals were identified for perfusion medium design: ease of use and cost-effective performance. Towards this end, the target was a chemically defined, animal origin-free formulation that omitted growth factors. The AGT format was chosen to support fast and simple reconstitution, and a 12-month shelf life was specified. The formulation needed to function both as a seed train medium and a production medium, capable of supporting high cell densities and productivity at a 1 VVD medium exchange rate. Lastly, the medium would, of course, need to support cost-effective scale-up. This covers our development goals, and at this point, I'll pass the baton to Jessica, who will cover some of the medium development steps taken to attain these goals and discuss some of our early beta testing results.
Thanks, Louise. Hello, everyone. I'm Jessica Nichols. I've been a scientist with Thermo Fisher Scientific for over 8 years, specializing in formulation development. I'll be reviewing aspects of the medium development process, as well as discussing some early beta results. We started the development of the formulation by creating a panel of 10 perfusion media. This panel was tested in-house via a spin tube model and by external alpha testers. This early work was important to stress the panel against the diverse cell lines and operating conditions. Additionally, the alpha results were evaluated for growth rate and performance across multiple perfusion applications. In the example shown, one of the alpha panel media demonstrated close to 300% performance increase over formulations designed for fed batch. The alpha tester was also able to sustain high viable cell density, as well as maintain cell-specific productivity, leading to production rate of 3 grams per liter per day. After selecting a top media panel candidate, a series of experiments were designed to further optimize the formulation. Instead of using spin tubes, we developed a spin-down perfusion-like method using the Amber 15. Each subsequent experiment further advanced the medium candidate. In addition to this, Omics work was used to supplement component selection and concentrations during the final design of the experimental phase. The center graph shows one of the experiments where the data showed a 160% productivity improvement over the controls. The graph on the right is an example of a principal component analysis which provided confidence that these metabolites are driving a statistical significance and should be incorporated into the formulation. At this point, the formulation was ready for initial beta testing and was challenged against an array of cell lines, operating conditions, and screening methods. In one of the more unique cases, a beta tester desired to boost their seed train using a mid-process switch to our beta perfusion medium. This experimentation was carried out in 2 of their different clones that were frozen, thawed, and tested in one of our chemically defined fed batch formulations at bench scale. The N-1 perfusion seed train was set up and perfused with the beta perfusion medium, forcing a mid-process direct adaptation. Although eliminating the adaptation prior to carrying out the cell culture work is not recommended, both clones transitioned well to the medium and were able to reach a desired cell density a full day faster than expected. The beta tester used a 1 VVD media exchange and a TFL for cell retention. In another case, a beta tester wanted to explore using concentrated fed batch perfusion process in order to improve performance of a lower producing cell line. There are 3 conditions shown here: S.U.B, is a simple glucose-only batch operation using their existing conditioned medium. The S.B condition is a fed batch operation that used one of our fed batch prototype media and 2x efficient feed C+. And lastly, ISB is a concentrated fed batch condition using the beta perfusion medium at 1.2 vessel volume per day and TFF used to retain the cells and product in the reactor. During the concentrated fed batch perfusion run, the beta tester cell line achieved greater than 120 million viable cells per mil compared to a peak VCD of 20 to 25 million viable cells per mil in the simple and fed batch conditions. The fed batch condition provided a very strong increase in the productivity compared to the simple batch condition. Additionally, the beta perfusion medium condition further intensified the productivity over the fed batch condition by nearly double. Some additional refinement to the beta perfusion medium continues. A look at recent in-house testing and guidance on perfusion medium screening will be presented next by Christopher.
Thank you, Jessica. Hi, I'm Christopher Brow, an engineer and scientist in the process development team and R&D lead for the perfusion medium project. I'll be reviewing our most recent in-house results, some best practices around evaluating medium with perfusion, and some final notes on the path forward. Perfusion medium has diverse needs depending on which cell line it is paired with and what process is used. To better support this, we've worked on this formulation to support different concentrations. A 66% dilute concentration is closer to typical fed batch media. This functions well for cell adaptation and maintains growth rate at lower viable cell density. A higher standard concentration oriented for production is designed to counter typical osmolality drop during demanding cell culture perfusion. The higher concentration also provides better medium depth to support sustained higher cell density and productivity at low to moderate medium exchange rates. The continuous perfusion run shown here is in bench-stirred tank reactors with ATF2 filters at 1 vessel volume per day medium exchange with bleed adjusted to actively target a 95% cell viability. Both conditions start in the 66% diluted concentration of the medium. The bottom left data set shows viable cell density in solid lines and percent viability in dashed lines. The blue condition, which shows early steady state behavior, is run using 66% dilute medium for the entire process. The red condition switches to higher medium concentration twice as osmolality drops, being brought up to 80% dilution and again to full concentration. Performing a concentration increase in this manner mitigates impact to cell growth, and in this case shows an increased growth rate in the red condition at full concentration. Cell bleed, the dashed lines in the upper right plot, is implemented to prevent cell density from reaching excessive levels. This avoids causing a strong nutrient imbalance and risk of cell viability dropping suddenly. Bleed starting point was determined by a sudden change in growth rate as cell density is rising. In this case, the bleed was started too early and too high in the red production concentration condition. This caused the percent viability to stay too high at around 98% and limited the initial viable cell density. The bleed rate was carefully reduced to bring percent viability to target steady state in the higher concentration condition and maintained from around day 30 to 42. This resulted in a steady state viable cell density of about 90 million cells per milliliter for the 66% dilute medium and 120 million cells per milliliter for the full concentration medium. The steady state productivity for this cell line was excellent. In a 14-day simple batch, it reached about 1.3 grams per liter. By comparison, in steady state for this run, it was over 1.7 grams per liter per day in the full concentration and over 1.2 grams per liter per day in the 66% dilute medium, which is similar to the difference in medium concentration. The steady state osmolality, which is not shown here, is about 300 milliosmo and 255 milliosmo respectively for the different concentrations. It's likely that running at such a low osmolality in the dilute medium caused stress to the cells and may explain a stronger ammonia production rate, which is also not shown here. When comparing run conditions, it is important to consider cell size. The bottom right plot takes into account cell size by showing viable cell volume in the solid lines and productivity per viable cell volume in the dashed lines. When we look at viable cell volume being maintained between the two conditions, we can see that the growth rate falloff that was used to determine starting bleed occurred at similar viable cell mass. This may suggest cell signaling was a primary factor. Additionally, the upper right solid plot lines show cell productivity based on viable cell density, suggesting a difference in productivity in different points in the run and relative to the two conditions. However, when looking at productivity per viable cell volume, the two conditions are almost perfectly in alignment during the entire process, a very different picture than what we see when focused purely on viable cell density. Evaluating a perfusion process and medium to be used with it provides a lot to consider. The best practices I bring up here deserve more than the time I give them. First and foremost, a good test setup gives you results that are meaningful with respect to your process goals. The table to the upper right shows 4 different ways to think of agitation and some of the typical operating regions that it falls into. Understand what parameters you will need to scale with your model and also where you can be flexible. Separately, know where your quality needs to be and what governs it to establish control boundaries in your run. It won't only provide a path towards optimization, but it will also level the field when comparing different media and operating conditions. Second, when preparing media conditions for a run, supplements are often added. Some cell lines have complex or specialty components present in the medium they were developed in. It's advisable to make sure that these are present in all conditions tested. Also, when performing supplementation for perfusion, components that normally accumulate in medium are continuously removed and may need to be added back at higher concentration. Conversely, components that accumulate in the cells themselves must be considered very carefully, as their continuous addition may overwhelm the cells. The lower left figure shows results of greatly changing cell demand for L-glutamine during a run, causing control difficulties. Third, always adapt the cell line to new medium conditions before testing. Ideally, make sure your growth and productivity are stable. Similarly, if you want to perform a mid-process media change, including concentration or supplement changes, see how it behaves in flasks first so you have an idea of what to expect. Flasks are cheap. Reactor runs are expensive. Fourth, know the limits of your cell line. Some cell lines lose productivity fast when selective pressure is removed. Some do not behave well at higher VCD, either due to increased collisions and signaling or due to physical operating stress of a more aggressive environment, particularly heavy gas sparging. The plot to the bottom left is from a cell line stress run with ramping agitation up to 600 RPM. The cell line handled this and other stress tests very well, but the production stability made it a very poor candidate for our continuous perfusion testing. Depending on your process and cell behavior, you may need to run a longer screening duration. In this intensified fed batch, 2 conditions based on the cell health profile to the left appear to be identical. By running out past 15 days, we saw that they were very different in late run on the productivity profile to the right. It also showed us we had buildup on our filter by sampling both from the reactor and the permeate. In many cases, a screening run seems to be at steady state, but in reality, the cells simply haven't had enough time to start dying yet. Screening medium for a continuous process is particularly difficult to model with short screening. Again, based on the cell health profile, we assume both conditions are similar. If we only ran 15 days, medium A would be the clear choice, and it looks like steady state has been achieved. However, as medium components get reduced in towards their final steady state concentrations, medium B productivity jumped upwards and stayed there the rest of the run, giving a much higher net titer. By comparison, medium B got a similar boost, but then lost productivity. This cell line also had lactate cycling oscillations, which complicated hitting steady state early. We're currently in the middle of our second beta test round. We're also continuing to investigate different scaling models and their limits, as well as testing with medium concentrations and room temperature stability to support a catalog perfusion medium launch next year. For more information on that, you can follow up with the product manager, Ian Dillon. There's much more to be done after launch, and we intend to continue collaborating with customers and build on what has been learned and push the limits of what we can provide. On behalf of the Grand Island R&D team, we hope you enjoyed our presentation section, and we expect the demands of perfusion to grow. Our work on this medium is our first step towards supporting our customers' perfusion process to make the world healthier, cleaner, and safer.
Hello everyone, my name is Alex Boscolo. I'm a field application specialist for single-use technologies, Thermo Fisher Scientific, based in EMEA. And the topic of my talk today will be scaling up perfusion, perfusion processes in single-use bioreactors. So it's going to be a little bit of information of how at Thermo Fisher we designed and developed a specific solution for perfusion processes that are advancement over the traditional single-use bioreactor setup that we have for fed batch or traditional batch processes. So in order to understand a bit better how we came to the solutions that we have, I would like to give a little bit of history of how the S.U.B single-use bioreactor came to be. So originally, it was really designed as a one-to-one copy of the stainless steel bioreactors that had been used in the industry for decades. It was trying to mimic as much as possible the structure, the hardware, the mixing, and the way of processing in a stainless steel bioreactor. So we had a typical 2-to-1 aspect ratio for cell culture, 1 to 3 impellers, depending. Well, the stainless steel bioreactors could have 1 to 3, but for cell culture it was usually 1 impeller with a 1/3 diameter compared to the vessel size. And it was traditionally, again, a pitch blade for cell culture with direct drive. And we developed a single-use bioreactor, either with, of course, with temperature control, either with a water jacket that would be able to heat and cool the system, or just an electrical heater for simple cell culture applications that didn't require cooling. Again, when it came to sparging, we tried to mimic as much as possible the options available for the stainless steel bioreactors, using micro spargers, so the typical Fritz sparger, as well as larger spargers for larger bubbles for CO2 stripping. There are, of course, a few differences from the beginning compared to stainless steel bioreactor. The main one is the absence of baffles, which are not particularly handy to design in a single-use environment, and the positioning of the stirrer. It's off-center, it's at an angle. It's been designed from the beginning to sort of make up for the absence of baffles and still allow very efficient mixing in a single-use bioreactor. Of course, we started on the market, it was around 15 years ago now, with a 50 to 150 liter sub. And of course, over the years, there has been many improvements, many changes to the design. So the basic has remained the same, but of course, there has been definite improvements. So we've scaled up the bioreactor up to 2,000 liter size, launched in 2010. And one of the most important things that we've launched in the last few years, it was a drill hole sparger, which was a specific sparging technology designed for low shear and for very scalable oxygen and CO2 mass transfer, as well as balance. So it was designed as instead of having a micro sparger and a macro sparger, to just work with a single drill hole sparger that could do both functions at the same time. And it was so efficient, so successful, that it led us to development of the 5-to-1 HyPerforma sub, which means we were now able to have a 5-to-1 turnover ratio scaled down up to 20% of the total working volume of the vessel. Drill hole sparger and the patented cross-flow sparger were the main innovations that allow us to successfully launch the 5-to-1 HyPerforma single-use bioreactor. Of course, now the topic of this talk is perfusion systems. So we have a lot of experience with perfusion, but at first we had to look at the different technologies available on the market and see, okay, what's available there, what our customers are doing, And do we agree it's the best way of doing it, or is there something better that we might be suggesting to customers? So there's multiple technologies available on the market. Spin filters, they were a traditional one, but they're limited to stainless steel bioreactors, so it was easy to dismiss them. And of course, tangential flow filtration and ATF, they are two very similar technologies. The ATF is sort of an evolution of the TFF. It's the industry standard because it allows very, very high cell retention, up to 100%, and especially the ATF is not particularly prone to fouling of the filter membrane. We've tried other technologies like ultrasonic separation, which had the advantage of limited to no fouling, but lower cell recovery was the main downside of it. So we came to the conclusion that what's the market standard is really, and in the current status of technology, the best solution available. So all the work we've done so far has been with ATF and TFF as perfusion technologies. Many of our customers, they've started applying a TFF or an ATF filter to their single-use bioreactors, and they just work with that, and they were happy with it. But of course, with perfusion technologies come different challenges that sometimes were not easily solved with a traditional single-use technology. The most important ones are the higher mixing power that's required when you want to keep very many cells in suspension and in an homogeneous solution and provide enough mass transfer. Then you need a much higher power input than what's normally available on a sub. You need, in general, higher mass transfer, especially for gases. So gas transfer is often the limiting factor. Oxygen, KLA tend to be an issue when you work with very, very high cell densities, of course, because the oxygen demand of a culture with 100+ million cells per milliliter is different than when there are 5 million, 10 million cells per milliliter. And of course, something that might sound trivial, but in the world of single-use technology, it isn't necessarily so, is the ability to connect your system to an ATF or a TFS system in an efficient way, in a sterile way, in a way that allows optimal manipulation of the system. So we did a lot of work in our R&D to make sure that all these requirements were met. And this is something that the first thing we tried really helped was moving away from the standard impeller size that would be 1/3 of the diameter of the vessel. We saw that simply by scaling up the impeller size, so for example, in a 100-liter bioreactor, we would use a 250-liter sized impeller, we would reach much higher power input. And this really allowed to meet the target that we set for our testing, that was at least 100 watts per cubic meter of power input in the vessel. With a traditional system, we are limited to 20 to 40 watts per cubic meter. We were able to scale it up to at least 100, even more depending on the bioreactor size. So that was very successful at those scales from 50 to 500 liters. Having a larger impeller, of course, comes with downside or just the consideration you have to keep in mind that when you're scaling up, we've seen it before, one of the parameters that you could look at is power input, but you could also look at tip speed. And of course, you cannot just scale up keeping the same impeller speed for larger impeller, because then your power input will be different, your tip speed will be different, your shear will be different. So it does require a little bit of extra planning and just reducing the stirrer speed as necessary to maintain the scalability of the system. The second limitation that we've worked on is the oxygen mass transfer. This is especially a work that we've done together with a customer. They were using our single-use bioreactor with a drill hole sparger as well as a traditional frit sparger. And their idea was that since the drill hole sparger made larger bubbles and the frit sparger would give very, very small bubbles, most of the oxygen transfer would come from the frit sparger because of the higher surface to volume ratio. So they've actually asked us to add a second frit sparger to the bioreactor, and we've done some tests for them. We've done dynamic KLA testing in a 500-liter single-use bioreactor, and what we've noticed is that even using two frit spargers and having a gas flow that was almost double as what's normally used in a single-use bioreactor, that would be 0.1 vessel volumes per minute, their oxygen KLA did not really show a dramatic increase. So working at 20 liters per minute of oxygen through 2 different spargers, they would achieve 36 KLA per hour. Going up to 0.2 ppm, they would just reach 41, 42 oxygen KLA per hour. So really not a significant improvement. And when we decided with them to try an alternative, we've had much better results. What we've done is just redesign the drill hole sparger to sort of combine the fluid sparger functionality as well as the normal drill hole sparger functionality. So we made smaller holes, a higher number of them, working at 0.2 ppm, and we've noticed a 2 to almost 4 times increase in KLA using only the DHS, which means a very significant improvement in the oxygen transfer, which did not influence negatively the CO2 stripping, which is the parameter that you need to keep balanced with oxygen transfer to make sure that there is the right amount of CO2 available in the system. And we've done this kind of work at every size from 50 to 500 liters, so 50, 100, 250, 500 liter bioreactors, and we ended up using different sized drill hole spargers with different holes in there at every size of bioreactor, so that it would be the perfect size of bubbles, the perfect amount of bubbles for this specific bioreactor. And that's what we call the enhanced DHS. That's specifically for very high cell density cultures like perfusion cultures. Other than the back design that we've looked at so far, we had a few hardware enhancements as well for perfusion. So normally with perfusion culture, working at 5:1 turn-down ratio, it's sort of a nice to have, but it's not top priority. So we prefer to move back to a lower turn-down ratio, but using an upsized impeller and making sure that the mixing was as possible, so that mass transfer inside the system would be the best that we could achieve. So in some cases, we actually call it a 4:1 turn down, so that you would have still a longer impeller, a longer drive shaft than on a traditional legacy system, but not as deep in the system as a 5:1 turn down ratio unit. In addition to all the improvements of the system that we've seen so far, there are a few points that I would like to highlight in the design of the consumables for a perfusion run, for a perfusion bioreactor. Talk about the enhanced drill hole spargers already. The fluid sparger is still available as an option. We don't think it's strictly necessary, but it does give a little bit of extra capabilities to the bioreactor. And especially if we're working on a perfusion process that's already mature, and you want to change it as little as possible, and it's still working with a fluid sparger, then it's definitely still a possibility. Upsized impeller we've discussed already. Of course, with perfusion culture, one of the critical things is that it's more prone to foaming than a batch or a fed batch process. So we've implemented a single-use foam sensor for automated anti-foam dispensing. So the users won't have to continuously keep an eye on the bioreactor to make sure that there's no excessive foaming, or even a certain amount of anti-foam just to prevent foaming. Then it can be controlled and only add the anti-foam when it's really needed by the system. We've added in the front of the bioreactor an extra port for cell bleed. Again, we've seen before, with perfusion bioreactors, it's important not only to be able to maintain, to reach a certain cell density, but it's also you need to be able to maintain it. And sometimes if the cells grow too much, then you just want to have a little bit of cell bleed to keep the system in a proper steady state at the desired cell density or viable cell density set point. And definitely mentioned it before again, 1-inch ID, ATF or TFF connections, so that the flow to and from the bioreactor to the ATF and back would be large enough to maintain a proper perfusion process running, even at larger scale. So to verify all the improvements that we had with our single-use bioreactors, we've run a number of different tests. ourselves and with our customers. And these are some results on a 50-liter bioreactor that we could also easily scale up to 500 liters. And it's more of a proof of concept than everything. So it's really just to demonstrate the functionality of a single-use bioreactor for perfusion cultures. So the idea here was to run the bioreactor and have different set points of cell density and during the run, and just verify that the system would be able to maintain them. So we started at about 50 million cells per milliliter. Then after a few days, we moved to 100 million cells per milliliter, then 150, then 200 million cells per milliliter. And we were able to demonstrate that the system was maintaining the cell density at the desired set point. Eventually, what we've tried to do, we just let the system grow. We let the cells grow without any control to see what would be the highest cell density that we would achieve. And we just ended up at over 260 million cells per milliliter. At that point, we just had to stop the run, but we are confident that theoretically, at least, the system could achieve even more, thanks to all the advancements that we've seen so far. So one of the things quickly mentioned now during this talk, the turndown ratio. Of course, when you scale up processes, you want to go as quickly as possible to your final bioreactor, so that you don't have to waste a lot of time and effort in your seed train. So with a 2-to-1 turndown ratio sub, then to end up on a 500-liter bioreactor, there will be a large number of steps from flasks to a rocker bioreactor to a small sub, then possibly an intermediate sub, up to the 500-liter bioreactor. With 5-to-1 turndown ratio or 4-to-1 in case of perfusion, then it's easier to scale just from rocker to an intermediate sub to a 500-liter sub. I'm saying 500, could be 1,000, but the concept is that 5-to-1 turndown ratio gives you a shorter seed train. But what if we could reach 20-to-1 turndown ratio or 10-to-1 turndown ratio at least? Then you would be able to go straight from a rocker bioreactor to a 500-liter sub, or from a shake flask to a 50-liter sub. Now, this is something that I'm really excited to show because it's something very new. With pleasure that I have the chance to introduce Thermo Fisher HyPerforma DynaDrive single-use bioreactor. So the DynaDrive, it really is the next generation of single-use bioreactors by Thermo Fisher Scientific. We took all the knowledge we had designing, developing, and working with our customers with our single-use bioreactors, and we put all of that into the design of the DynaDrive. So it's really been designed from scratch to be the most efficient single-use bioreactor available on the market. It will be available from spring next year. It's already been introduced to our American customers very recently, and it will be introduced at BPI in Frankfurt to our European customers next month. And it's a very exciting new product. So the Thermo Scientific DynaDrive is really the new single-use bioreactor that's been designed, developed by Thermo Fisher in order to tackle the highest, the most difficult requirements of any user of single-use bioreactors. It doesn't really replace the HyPerforma. It's just an addition to the traditional HyPerforma sub product range for the very, very demanding applications. The applications that require mixing at very low volumes, that require very low turndown ratio, 10-to-1 for the 50-liter sub, up to 20-to-1 for the 500-liter sub, which really allows you from seeding from flasks into a sub, a small one, or from a rocker bioreactor into a 500-liter sub. And it's been designed and optimized in order to have the highest power input per volume and the highest KLA available on the market. So to work with fed batch, of course, but definitely for perfusion cultures that require a very high cell density and high oxygen demand. It's very scalable between the 50 and the 500 liter sizes. And it does, of course, allow our customers to have noticeable savings both in CapEx and in OpEx due to the lower amount of bioreactors required for the seed train. So it's cheaper to run, it's very efficient, and it improves the footprint. Any facility allows a lot of available space to be used for something else than just running bioreactors. It's a new system. It's been recently shown to our American customers. It will be shown in the near future at BPI in Frankfurt to our European users, and should be available in spring next year for customers to actually have in their labs. And you can see more information about it on the website thermofisher.com/DynaDrive. And with this, that's the end of my presentation. Thank you.
So hello everybody, thank you for attending this webinar about continuous bioprocessing. My name is Pirkko Mohonen and I work as a field application specialist at Thermo Fisher Scientific, and I'm specialized in cell culture medium and liquid solutions in bioproduction. So as our webinar focuses on continuous upstream cultures, I want to highlight here that perfusion technology really changes the needs of liquid supply in the bioprocess. In continuous process, the culture media is perfused constantly, which creates a different liquid supply need compared to a batch or fed batch cultures. So often the total media volumes are very high because the process is running continuously over several weeks. I will spend the next 10 minutes to give you an overview of our large volume liquid capabilities and solutions at Thermo Fisher Scientific. I will start by introducing our media manufacturing capabilities. Thermo Fisher Scientific's bioproduction Gibco cell culture media network is comprised of 2 redundant sites in US and Europe. This media network services the globe with all 4 of our formats, consisting of dry powder media, advanced granulation technology called AGT, single media and buffers, and also concentrated media and buffers. Our products are currently used in over 110 commercial therapies, and customers can rely on our global operational excellence for their assurance of supply. So moving the process to a continuous bioprocess is an opportunity for the bioprocessing company to reassess the efficiency of how they make the liquids available for the bioprocess. So on this slide, I will go through the advantages and benefits to outsource the bioprocess liquid manufacturing. So for example, the advantages are the better product consistency. There are fewer contamination risks by simplifying the process. And it also helps to decrease operating costs by eliminating the labor-intensive steps like QC, liquid preparation, filtration, quarantine testing, documentation, and validation procedures. So this will free up some skill staff as well as space. By utilizing the advantages of outsourcing bioprocess liquid manufacturing, you're able to realize cost savings, have improved quality and compliance, and resulting in overall increased productivity. So whether you are looking for an economical standard product solution or require a specific custom design system, we offer proven bioprocess liquid solutions at every scale. So we do have strong liquid production capabilities, and we have combined these capabilities with our worldwide supply chain distribution centers, DOE and Ingalls logistics, which are based both in US and Ireland. So DOE and Ingalls GMP supply chain services can help us, for example, to deliver your goods on time and manage back orders. These services aim to increase the customer's productivity and also reduce costs by offering, for example, GMP chemical storage, increased lots, and consolidated shipments. We provide certified clean rooms and quality specialists for sampling, which is also to help you to decrease the key expense drives. So we have developed a robust internal infrastructure so you can receive dependable, high-quality products that are designed to meet your bulk liquid and buffer requirements. You can choose from ready-to-use cell culture media, media supplements, buffers, and other process liquids packaged in a standard and customized bioprocess containers, all from 1 liter to 1,000 liters, from the manufacturing facilities located in Grand Island in New York and at Paisley in Scotland. I quickly show here an example how outsourcing bulk liquid manufacturing, in this case, outsourcing 40,000 liters on sodium hydroxide buffer, has led to significant annual savings. So this study shows how attractive the economics of outsourcing can be, simply based on the larger batch sizes that are achievable through the use of an outsourced partner. The five-fold increase from 2,000 liters to 10,000 liters in batch size translates into significant annual savings, as well as reduction in preparation times, lot testing, and per liter cost. If you like to preview your large volume liquid manufacturing costs, we are here to help you to identify the cost drivers for fixed, variable, and consumable costs. To help making the decision, we have developed a cost analysis model, which can help you to make a more rational decision on what can be outsourced and what must be kept as a core business. We can position ourselves as the neutral advisors, and we can help you to go through the whole cost analysis. We can supply both large volume liquids as well as technologies to hydrate and prepare medium and buffers internally, such as single-use mixers and various formats from the ready-to-use AGT or concentrates to dry powder medium. So far, I have introduced you to our large-scale liquid production capabilities and benefits of outsourcing the liquid preparations. We also offer cell culture medium in dry powder formats. Since 1970, Gibco has been producing dry powder medium, and in 2004, our engineers developed a proprietary powder format called AGT for advanced granulation technology. AGT is widely used in production because it's very easy to use in large scale. Some of the advantages of using AGT are, for example, on improved storage capacity and generally longer expiration dates than the liquid medium, which gives more flexibility in terms of the management. I also wanted to mention here that the perfusion medium discussed during this presentation is currently available as AGT format, but can also be delivered in liquid format as a custom product. So for the customers who choose to hydrate and mix the culture medium or buffers in-house, we can offer our Gibco water for injection as a part of our core competence. In this slide, I want to highlight the process of producing ultra-pure water that we use also in our own medium manufacturing processes. So the process uses drinking water, which is then filtered by 0.1 micron filter and deionized. The water is pre-treated with activated charcoal and double distilled with 3 distillation units. The capacity of producing high-quality water is 2,000 liters per hour. So the end product is stored in stainless steel tanks for several thousands of liters until these are used in production. And the water quality is monitored routinely, for example, conductivity, total organic carbon, metals, endotoxins, and bioburden. So if you don't have WFI system in-house or you don't have high enough capacities, Gibco WFI is a part of our core LVL solutions, and it is available in 20-liter and 200-liter sizes. So I have introduced you to our dry powder formats and ultra-pure water capabilities. On this slide, I wanted to bring to your attention the full picture of the medium mixing solutions we can offer for you, especially when the perfusion technologies increase in the needs of higher medium volumes. So we have mixing solutions starting from the 30 liters always up to our Impulse 5,000 liters, which is at the moment the world's largest single-use mixer. So to bring this presentation to the end, I want to summarize on this slide our bioprocessing liquid solutions that are available to support your continuous bioprocess. So depending on your requirements, the decision to internalize or outsource bioproduction liquids should be done according to a rational approach of the cost calculations and risk analysis. So when you choose to outsource liquid manufacturing, Thermo Fisher Scientific can supply liquids in large quantities in bags and containers that are designated to be compatible with your process. And if the outsourcing of the liquid manufacturing is not the preferred option for you, and you wish to maintain this on site, Thermo Fisher Scientific offers a range of single-use mixers, bags, different medium formats, and express services. This purpose is to facilitate the large-scale use and to optimize the liquid preparation. So this was all for today, what I wanted to talk about the bioprocess liquid supply strategies to support continuous bioprocessing. So thank you for listening.
Thanks very much, Pirko, for providing us with those valuable insights about the liquid supply strategic implications in successfully implementing perfusion. You've enjoyed learning about all those sides of this exciting and hot technology. Before we wrap up the webinar, we would like to open the floor for a few questions. Okay, well, thanks for your attention. So you may have noticed on the right-hand side of your event screen that there's an opportunity for you to ask questions to get our panel to respond. I'll leave you a few minutes to do this. We do have a first question in the meantime, and that question is maybe for Alex Boscolo. So the question is, obviously, the perfusion bioprocesses are relatively complex with ins and outs. They last for a long time. Media needs to be added, which requires controlling. So the question is, what options are out there in order to be able to automate perfusion processes, and can some best practices be identified?
Yeah, that's a very good question, because indeed perfusion processes tend to require a higher degree of automation than traditional batch or fed batch processes, because there's more moving parts involved. So as Thermo Fisher Scientific, with our single-use bioreactors, we've always been using an open architecture approach. So it doesn't necessarily, we're not linked to any specific way of controlling our bioreactors, as long as the customer is happy with what they're doing. But of course, we do have our own HyPerforma line of controllers for single-use bioreactors, which have been especially developed in combination with our S.U.Bs, and therefore are in our idea the first choice when it comes to controlling a single-use bioreactor. There are many options available, and definitely we do have experience, a lot of experience with perfusion bioreactors. So we have developed specific strategies that we can implement with our HyPerforma bioreactors and HyPerforma controllers, and that's definitely one thing that we can discuss together in more detail with any customer that's interested in knowing more about the HyPerforma line of controllers.
Thank you so much, Alex. We can take more questions if attendees wish to use their question submission boxes. Okay, so anyway, I think that does in the absence of further questions from the audience, I think this does wrap up this webinar. So thanks everybody for the time committed to this discussion, and all the speaker details can be obtained. Feel free to visit our website, and if there's anything that Thermo Scientific can do to help you robustly implement continuous upstream bioprocessing through perfusion, we'll be happy to help. We hope you enjoyed this webinar and you found the content educational, and we wish you a great rest of the day. Thank you.